So the rest of today's lecture will involve the discussion of scattering from a step potential in one dimension. So in physics, especially in quantum mechanics, an important problem is to consider how quantum states scatter from a potential. So in one dimension, let us treat the most simple case. So what we are going to do is that we are going to discuss the case where we have some potential, which has it has a form like that. So this is the x-axis, and the potential has value 0 for x. So this is the origin. So for the negative values of x, the potential has value 0, and for the positive values of x, the potential has some constant value v0 or v0. So of course, realistic potentials do not have this form. They don't have discontinuity. So realistic potentials are more like, they'll just go like this. They have their 0, and then they will increase to some stable value over some range. Okay, so, but the step potential is a convenient mathematical idealization. So, because if you can understand the step potential, qualitatively, we'll be able to understand what's happening for realistic potentials. So before we discuss the quantum mechanical scattering, let's discuss, or let's remind ourselves what would happen if this was a classical scattering problem. So in that case, there are two scenarios. One scenario is that the energy of the particle, so what we are assuming is that there's a particle which coming in from the left, and then it's scattering of this potential. And in that case, there would be two cases. In one, the energy of the particle would be greater than the potential barrier. If that is the case, then in classical physics, we would expect the particle to continue on, although its kinetic energy would be reduced when it continues on to the positive x-axis. It'll be reduced by this amount, v0. And in the second case, where E is less than v0, we would expect the particle to come up, and then it would then its potential energy would its kinetic energy would be transformed into potential energy, but its kinetic energy would not be enough to overcome the potential barrier, so it'll turn back and it'll bounce back. So in the second case, we expect the particle to be reflected. However, in quantum mechanics, this is not the case. So for definiteness, in this lecture, we are going to consider the first case for quantum mechanics. So what's going to happen in quantum mechanics? To analyze it, we will take a wave packet. So we will take some wave packet, initial wave packet, which is a Gaussian. So the analysis that we will develop will be independent of the explicit shape of the wave function, but for definiteness, we are going to take a Gaussian. So what we're going to assume is that we have some Gaussian that is incident on the potential barrier, and the energy of the wave packet is greater than v0. And then what we expect is that after a while, because of the wave nature of quantum mechanics, after a long time, so after the Gaussian has come and hit the potential barrier, we expect that there would be a reflected wave. And there would be reflected wave, something like this. And so this would be psi of r, and then there would be a transmitted wave which will go through, and this will be psi of t. And because the normalization of a wave function is independent of time, if you look at the probability density associated with this Gaussian, the integral over the probability density would be equal to 1. And similarly, the probability density that is associated with this guy and this guy would also be 1. So let's make these ideas more definite. So let's start with a Gaussian, which is going to be our initial state. So, and let's take our initial state to be the wave function of the system at time 0. So this is our initial state. And we take that initial state to be a normalized Gaussian whose energy, who has an average momentum of h bar k naught. So the Gaussian has this form. So this is the phase factor associated with its momentum. And this is the Gaussian part. So this means that this Gaussian at time t0 is centered at this point, and x at this point is minus a. And the spread of the Gaussian is given by this delta. So we are going to assume that this Gaussian is very spread out in position space. So it's quite spread out in position space. But in momentum space, it is very sharply peaked. So it's very sharply peaked in k space. Its momentum, its average momentum is around h bar k naught, and we're going to assume that is very sharply peaked. So this means that it's actually very spread out in position space. And then what we're going to, so at t equals to 0, our system looks something like this. So this is t equals to 0, and our Gaussian has is something like that. And this is minus a, and then, it's moving in that direction. And after a long time, where t is much greater than the time it took for the Gaussian to go and hit the wall. And what is that time? That time is given by am over p naught. And so in a time scale which is much larger than that, the wave function will be split into two parts. There'll be the reflected part, which will be moving in that direction. Let's call that psi r. And there would be a transmitted part. And that will be called psi t. The uncertainty in the position and the momentum of the initial wave function is given by, because it's a Gaussian, and this confirms the statement that we made before, that if the uncertainty in the position is very large, if delta is very large, then the uncertainty in the momentum is very small. Because the initial momentum of the particle, of the wave packet, is p naught, and that's given by h bar k naught. So the time that it'll take roughly for the initial wave function to reach the potential step is going to be given by t will be something like m times a over p naught. And long after this, we will have this kind of scenario. So the problem that we have to solve is this. The problem that we have to solve is to find out what the reflection coefficient is. The reflection coefficient is defined as the probability that the wave was reflected. So that would be given by the reflected wave function squared times dx, integrated over all space. And this is called R is called the reflection coefficient. And we also have to find out what the transmission coefficient is. That is the probability that the wave or the particle would actually be transmitted This is called the transmission coefficient. So what does this mean physically? Physically, what it means is that even though the energy of the particle is greater than V naught, there will be, we'll find out, a non-zero probability that the particle will be reflected. And of course, there will be a non-zero probability that the particle would be transmitted. So this is very different. This expectation is very different from the classical expectation. For the classical expectation, if the energy of the particle was greater than V naught, we would only expect it to be transmitted. There would not be any chance of it getting reflected. But in quantum mechanics, there's always a chance, finite chance, that it'll be reflected. So this is something we'll see in this lecture.